Hello guys, in this problem, we are given a 2D grid where each cell contains either x, y, or a. Our task is to count how many submatrices satisfy certain conditions. Let's break it down in a simple way. First, what is a submatrix? A submatrix is any rectangular section of the grid. It can be small like a single cell, or larger covering multiple rows and columns. Now, for a submatrix to be valid, it must follow three conditions. The first condition is that the submatrix must include the top left cell of the grid, which is grid 0, 0. So we are only considering submatrices that start from the top left corner. The second condition is that the number of x and y characters inside that submatrix must be equal. For example, if a submatrix contains 2x and 2y, it satisfies this condition. The third condition is that the submatrix must contain at least one x. So even if the number of x and y are equal, if there are 0x, we do not count that submatrix. Now the goal is to go through all possible submatrices that include the top left cell and count how many of them satisfy these conditions. In simple terms, we are expanding a rectangle from the top left corner and checking whether the count of x and y is equal and there is at least one x present. This problem mainly tests your understanding of matrices, submatrix enumeration, and counting frequency efficiently. That's the overall idea of the problem. Let's go through each example carefully so the idea becomes very clear. First example. The grid is x, y, y. We only consider submatrices that start from the top left cell, which is x. Now, let's expand the submatrix step by step and check the conditions. Take the first cell alone. Submatrix is x. Number of x is 1. Number of y is 0. They are not equal, so this is not valid. Now take the first row up to the second column. Submatrix is xy. Number of x is 1. Number of y is 1. They are equal, and there is at least one x, so this is valid. Next, take the first row completely. Submatrix is xy. Number of x is 1. Number of y is 1. They are equal and there is at least one x, so this is valid. Now expand to include the second row and first column. Submatrix is x, y. Number of x is 1. Number of y is 1. They are equal and there is at least one x, so this is valid. Now check larger rectangles. If we include more cells like xy, y. Number of x is 1. Number of y is 2. Not equal, so not valid. Similarly, any larger submatrix will not satisfy the condition. So the total valid submatrices are 3. Second example. The grid is xx, xy. Again, we only consider submatrices starting from the top left cell. Let's check possible submatrices. Single cell, x. X count is 1. Y count is 0. Not equal. First row, xx. X count is 2. Y count is 0. Not equal. First column, x. Again, not equal. Full grid, xx. xy. X count is 3. Y count is 1. Not equal. No submatrix has equal number of x and y, so the output is 0. Third example. The grid is. There are no x characters at all. Even though the number of x and y could be equal as 0 and 0, the condition requires at least one x. So none of the submatrices are valid. Hence, the output is 0. We need to count the number of submatrices that start from the top left corner and satisfy two conditions. The number of x and y should be equal, and there must be at least one x present. Let's understand how this optimized solution works. Instead of generating all possible submatrices and checking them one by one, which would be very slow, this solution uses cumulative counting to efficiently track the number of x and y. We start by initializing two arrays called cumulative x count and cumulative y count. These arrays keep track of how many x and y characters we have seen so far in each column, considering all rows up to the current row. Now we iterate through the grid row by row. For each row, we maintain two variables, current row x count and current row y count. These variables track how many x and y we have seen so far in the current row from the first column up to the current column. As we move from left to right across the row, we update these counts. If we see an X, we increase current row X count. If we see a Y, we increase current row Y count. Now comes the key idea. For each column, we add the current row's counts to the cumulative counts. So, cumulative X count at a column stores the total number of X characters in the rectangle from the top left corner to the current cell. Similarly, cumulative Y count stores the total number of Y characters in that rectangle. At this point, for every cell, we are effectively considering the submatrix that starts from the top left corner and ends at that cell. Now, we simply check the condition. If cumulative X count equals cumulative Y count, it means the number of X and Y in this submatrix is equal. We also check that cumulative X count is greater than 0 to ensure there is at least one X. If both conditions are satisfied, we increment our result. So instead of checking every possible submatrix explicitly, we are only checking submatrices that start from the top left corner and end at each cell, which matches the problem requirement. This makes the solution very efficient. Let's run this solution. And yes, all test cases pass successfully. Now let's submit this solution. Hurrah, the solution passes all test cases successfully. That's it for this problem. We solved it using a prefix sum approach to efficiently track counts of X and Y without checking every possible submatrix. This pattern of reducing a 2D problem using cumulative counts is very useful in many matrix-related interview questions. Keep practicing similar problems to strengthen your understanding. Hit subscribe and like the video. See you in the next video.